So we implemented moment tensor potential and the active learning algorithm in this package. Several words about me. Okay, I have already been introduced, but should add something. So first, I was graduated from Moscow Institute of Physics and Technology 8 years ago, as I can calculate. Yeah, 8 years ago. Next, I defended my PhD in applied mathematics, but after defense decided to change my topic of interest, and since May, yes, work with Alex Shapeev in Caltech, but want to say that since December 2019 until July 2020, I was working at the University of Stuttgart in a group of Professor Blasha Grabowski. So it was something like a business trip there to Germany. Next, I returned back to Alex Group, and also since this year, since September of this year, I'm also something like instructor at Moscow Institute of Physics and Technology. So we are preparing the course on machine learning interatomic potentials in molecular dynamics in the whole. So also we'll speak there not only about MTP, but about GAP, about SNAP, about NNP, about all the most important potentials. So I'm instructor at MIPT. Okay, but let's move on to my presentation, directly to my presentation. Here is the plan. So it will be something like 20 minutes presentation now. So first, we'll talk about moment tensor potential. We'll introduce it. I will try to do it as simple as I can. Next, of course, I will talk about active learning algorithm, also important algorithm for training set construction. We have already discussed a bit today, as I heard, about training set construction. So active learning is important. And in the end of this presentation, I will tell several words about MLIP package. After these slides, we will directly go to deep node. So moment tensor potential. Let's start talking about moment tensor potential. If neural network potential is based on neural networks, Gaussian approximation potential is the so-called kernel potential. Moment tensor potential is the so-called polynomial potential. We will see it now. So this potential is local. I mean the one implemented in MLIP code, because mainly I will talk about MTP implemented in the MLIP code without magnetism. But if you have questions about magnetism, of course, we may discuss. But okay, MTP is local potential. So as usual in the local potential, we calculate energy of MTP as a sum of contributions. The V is contribution of each is atom in the system, and I is atomic neighborhood. So the function V, as already discussed, as it was already discussed today, it should be invariant here to atomic permutations, rotations, reflections, and also explain this stuff should be smooth with respect to atoms leaving and entering the interaction neighborhood. We'll explain this in the next slide. So what is V? V is expansion over basis functions B alpha. We will construct during the next slides, we will construct these functions. I will explain how to construct B alpha basis functions. And here C alpha are linear fitting parameters. So after fitting MTP, we will find these parameters. But as I mentioned, we should somehow construct basis function B alpha. How to construct? In order to construct, we introduce the so-called moment tensor descriptor. So first, some notations denote atomic neighborhood like this. We will need relative atomic positions and atomic types of central atom and neighboring atoms. And what is moment tensor descriptor? Moment tensor descriptor is equal to production. It is, first of all, it is sum over all G atoms, all neighbors. And this is production of a radial path, this f mu radial path, and angular path, where this symbol is outer product. So we multiply the relative positions new times, or didn't write here, we multiplied new times. So M mu nu is the so-called tensor. So, for example, tensor of zeroth rank is scalar, tensor of the first rank is vector, tensor of the second rank is matrix, and tensor of third and fourth rank we call really tensor of third or fourth rank or greater. This is so angular path. It describes the so-called many-body interactions. And here we have radial path. Radial path is calculated like this with formula 4. With this formula where C are radial fitting parameters, or the so-called, because F is radial path, we call these parameters radial fitting parameters. Next, T beta are Chebyshev polynomials. And we multiply these Chebyshev polynomials by the difference between cutoff radius and distance between atoms. So number, what is important, number of these radial fitting parameters is equal to this. So typically in practice, we use 5 or 6 radial functions. Typically we use 12 polynomial functions. We sum over polynomials. Typically we take at around 12 or sometimes 16 polynomials. And imagine we have binary system. So for binary system, we will have at around several hundred radial fitting parameters. Let's go to the next slide. So here is a moment tensor descriptor. Here is a radial basis example. So here I drawn 6 functions. As we can see, they start from here. Maximum value of these functions is somewhere here in the minimal distance. So of course we introduce minimal distance between atoms. And then this function tends to 0 when the distance between atoms is close to cutoff radius. So this is the so-called smooth cutoff. And this figure explains what I wrote here. So this function is smooth. Again, our function V is smooth with respect to atoms leaving and entering the interaction neighborhood. This is the figure, just example. Okay, we introduced moment tensor descriptor. Now, once we introduce moment tensor descriptor, we introduce the so-called level of moment tensor descriptor, which is equal to this number 2 plus 4 mu plus nu. This is the level of moment tensor descriptor, and we also will need a level of moment tensor descriptor product. Level of moment tensor descriptor product is equal to sum of the levels of moment tensor descriptors of each moment tensor descriptor. So, for example, if we have a very simple moment tensor descriptor like M00, we have second level because mu is equal to 0, nu is equal to 0. Here we see 2. Next, I also wrote some examples of moment tensor descriptors, or the levels of moment tensor descriptors here. In the first line, I wrote the so-called simple moment tensor descriptors. The second line is product or powers of simple moment tensor descriptors. And in the third and fourth line here, I also wrote more complicated moment tensor descriptors. For example, here is the so-called inner product or scalar product of vectors. The level of it is equal to 10. One more moment tensor descriptor is the so-called contraction of matrix or Frobenius norm, how we call it in math. So it's sum over squares of all elements. The level of this descriptor is 12, and one more example. The tensor of the third rank multiplies by the tensor of the second rank. After that, we obtain moment tensor descriptor of, we obtain vector after multiplication of this. And next, we calculate inner product. So also we can obtain one more moment tensor descriptor. Here were examples of moment tensor descriptors. Next, finally, we go to MTP basis function constructions. So by definition, what is basis function B alpha? B alpha is the so-called contraction of any number of moment tensor descriptors yielding a scalar. So actually here in these lines, I showed examples of contractions. So in a product of two vectors is contraction, in a not in a product, but the so-called contraction of matrices is also a scalar. And one more product of moment tensor descriptor is matrix multiplication of matrix by vector. After that, we obtain vector, and then we calculate inner product. So one more example. Thus, as we can see, level of basis function B alpha is equal to this value. And actually, as you can see from this definition, there is infinite number of basis functions B alpha. So we can introduce infinite number of basis functions B alpha. So to define MTP, we choose some left max in practice, choose maximum level and include in basis any function B alpha with level B alpha is less or equal than maximum level. So in practice, of course, we deal with not infinite but finite number of basis functions. So now we introduced the basis function, and the very last slide about moment tensor potential is the so-called MTP illustration. So again, firstly, we have atomic neighborhood with atomic positions. Next, we calculate the so-called radial functions. We also calculate outer products of relative positions. Next, we sum over all atomic all neighbors in the neighborhood Ni. Next, we obtain moment tensor descriptions, and next we choose some level max and calculate basis functions B alpha. And finally, we return back to this formula 2. Finally, we calculate, now we know basis functions B alpha, and now we know, after fitting, we know linear parameters, or even not after fitting, even during fitting. So with some parameters, we can calculate the so-called functions V. Once we calculated functions V, we can calculate MTP energy. And as you can see, this function is smooth. So we can also calculate forces and, for example, stresses of a system by differentiating. So here was MTP introduction, the so-called MTP description. Next, we go to fitting of MTP. I should show this formula, I think. So imagine we have something like DFT data. So energies, forces, and stresses calculated with DFT. And we also have energies, forces, and stresses calculated with MTP, as I explained above. And by fitting, I mean solving this optimization problem. So we minimize this loss function. This is loss function. We minimize this on the set of theta parameters. And here also WE, WF, and WS, the so-called negative weights. We'll tell them more when we go to deep node, directly to deep node. So this was a part about moment tensor potential. But next, here, I described something like passive learning. So imagine we have a good data set, and we can simply train MTP on this data set. We somehow created the offline, not online and not actively. And now, but we also have active learning of MTP algorithm. So In practice, we should somehow create training set, our training set, and active learning algorithm allows us creating training set. And yeah, by the way, what should I emphasize? As I have already told, MTP is polynomial potential. So when we deal with polynomial, we will have extrapolation on the configurations. Most likely we'll have extrapolation on the configurations that were not included to the training set. So this active learning algorithm allows us creating such a training set, such a good training set that after we feed MTP, we can feed MTP on this training set and obtain good MTP. And this training set covers the so-called whole phase space. So we can cover with this active learning algorithm phase space. So have different configurations in the training set. It's something like motivation. Now let's talk about algorithm. Let's introduce some concepts. The first concept is active set. So imagine we have training set of k configurations and the moment answered potential with m optimized parameters. So imagine we have initial training set, have initial moment answered potential. By active set, we define a subset, such a subset of m configurations from the training set that maximizes such a determinant. Here we calculate energy with respect to MTP parameters or the so-called gradients. We can do it. So here, this is the so-called active set. This is the first concept we need. The next concept we need to describe our active learning algorithm is the so-called extrapolation grade. So imagine, assume we have any simulation, molecular dynamics, Monte Carlo, or we simply relax atomic positions, something like this. And we have something like Scratch, and imagine we have current configuration or given configuration CFG stuff from Scratch. We should decide whether to include this configuration to the training set or not, or even whether to consider this configuration as the candidate for inclusion in the training set or not. For this aim, we introduce the so-called extrapolation grade, which we calculate with this formula. But the main thing I want to say is that this grade defines the maximal factor by which the determinant of matrix A can increase if a CFG star is added to the active set. So this is extrapolation grade. And of course, we talk that we deal with extrapolation if this number gamma is greater than 1. Otherwise, we deal with interpolation. So now we have concept of active set, the first important concept. We have a concept of extrapolation grade, the second important concept. And next is the third concept, the so-called two-threshold scheme. So we introduce two levels, the so-called levels gamma select and gamma break. Gamma select is typically equal to 2, gamma break is typically equal to 10. So, and here in this something like diagram, we show that if gamma here, gamma CFG is between, if the value of gamma of CFG is between 0 and 1, we deal with interpolation. If gamma is between 1 and 2, we deal with accurate extrapolation. Next, if gamma is between 2 and 10, it is something like reliable extrapolation. But we consider this configuration as a candidate to the training set. So we add this configuration to the so-called preselected set. And imagine again, we have atomistic simulation. Imagine we find we have such a configuration with such extrapolation grade. So we add this configuration to the preselected set, but continue molecular dynamics, for example, or relaxation. But if gamma is greater than gamma break, then we break an atomistic simulation and form such a matrix, such a big matrix of P capital is a number of number of configurations in the preselected set. Next, we merge this matrix with the active set, and next again run algorithm allows us finding the maximum the submatrix with maximum volume, as I have already told. So in this way, we recalculate active set. But it's better to show the scheme here. So again, we start with the initial training set, initial MTP. First, we construct active set, and we construct the so-called active learning state. I will show you in tutorial what is it. Then we run simulations, molecular dynamic simulations. Then we select or we collect the so-called extrapolative configurations, or probably I also call them preselected configurations, preselected set. Then once we break, we run selection of configurations. We select some configurations from the preselected set, it's selection. After that, we obtain selected configurations, and what is important, we run ab initio calculations or DFT calculations only for selected configurations, not for all the configurations, only for selected. So after these ab initio calculations, we have energies, forces, and stresses calculated. Next, we add these configurations to the training set, update training set. Next, we retrain moment tensor potential. And next, we obtain the so-called updated MTP. And we run these iterations, these active learning iterations, until preselected set will be empty. So I think that this is active learning algorithm. And next, okay, we are very close to finalize this theoretical part. Now I will tell several words about MLIP2 package. So was developed at Skoltech by Alexander Shapeyev, Evgeny Podrybinkin developed together with Alexander Shapeyev the so-called active learning algorithm. Konstantin Gubayev implemented the form of moment tensor potential. And I suggested the so-called concept of comments in the MLIP code and implemented other things. So there are 4 developers. What should I emphasize? MLIP2 package is available for free for non-commercial use, please, non-commercial, and no redistribution allowed. So please remember about this. To get the MLIP code, open gitlab.com account. GitLab, by the way, should also emphasize gitlab.com, this website. So let's go again from the very beginning. Yeah, gitlab.com, not GitHub, but GitLab. It's important. You should fill in the form, the register form. You may check it out. After you fill in the register form, you tell that you agree with these conditions, so non-commercial use, no redistribution allowed. After that, you can clone the code from the repository, but we don't have to do it in tutorial. In tutorial, I have already compiled both MLIP code and, by the way, yes, didn't write here. Here, we also have the so-called LAMPS MLIP interface, so we may run LAMPS with MTP code, with MTP potential, with moment tensor potential as interatomic interaction model. And we can also run active learning with LAMPS and MLIP. So I will show it right now. So here I want to stop with presentation and yes, add one thing again. One important thing here, we will talk about MTP without magnetic moments, but a week ago, finally, our paper about magnetic moment tensor potential, where we include magnetic moments in the functional form of MTP, was accepted to NPJ. I will share the archive, I suppose, I will share with you. But here again, I will talk only about MTP without magnetic moments, about official version of the code. So here we are, I think, finished this presentation. Let's start machine. And what do you think? Probably you will ask some questions about theory right now, or we will do it after tutorial. What do you think?
I believe after the tutorial.
After
So
the
that,
okay.
yes, so that if there is something popping up, we can speak about that.
Okay, I agree. Okay, so let's continue. Tutorial, so terminal. My tutorial is not, my tutorial is very specific, so I will show everything in terminal. I have no notebook, and yes, concerning, I suppose, future questions about IPython notebook, for the moment we don't have IPython notebook implemented in official version of MLIP, unfortunately, for the moment not. But if you need, I suppose you may run Max Hodop. So he has been graduated from EPFL. Probably some of you know this guy. So Max Hodop now work at Caltech in our group. He implemented something like Python notebook for MLIP. You may contact him. I will also share his email. But okay, let's go here. So here we have only, I need only 3 folders for tutorial. The first folder is MLIP2. This is the folder with the MLIP binary file compiled. I should tell some words about MLIP binary file. MLIP binary file is the so-called self-explanatory executable file. So we can type MLP and list. After we type MLP and list, we see a number of commands. So we have the so-called commands concept in this code. So for example, MLP, if we type MLP help, by the way, yes, with the help command, we can get information about the concrete command. For example, if we type MLP help train, we will say that MLP train command will train potential.mtp. In MTP format, we also will talk about this. On the training set in specific CFG format. So in this version, again, in this official version, we have no JSON format. We have our internal CFG format, but it's very simple. And we should specify options also here. I will show you later. So this is MLIP2. Here we see no source code. You will obtain source code.
Sorry, Ivan, can you please zoom a little bit? So increase the...
Increase, sorry, don't know how to zoom.
Maybe Control plus.
Control plus.
Yes.
Yeah.
Because in at least in my screen monitor is it's very small, and so okay, like this is maybe very fine for me, but if someone else. Okay, thank you very much. Sorry for interrupting you.
No problems. So now we go to untrained MTPs, very important folder. So in this folder, we have something like library or with MTPs. So for example, let's go to MTP number 8. Yeah, by the way, these numbers mean this maximum level. Yes, I have already shown in this presentation, lev max. Where is it? Yeah, lev max. This number means lev max. So this is MTP of 8th level. Maximum level of contraction is equal to 8. Let's consider this simple MTP. So the format is like this. It's text format. The first string MTP, the second string is version, potential name, species count. You may, of course, change this number of species. This is number of atomic types in the training set. Next, radial basis type, we use Chebyshev polynomials. Next, minimal distance between atoms in the training set. We also may change this parameter. Next, max dist. Next, radial basis size or number of Chebyshev polynomials. So these lines we may check. These lines until which line? Until line 9 we may check, but the next lines starting from 10, please don't change. So these lines are fixed. These lines are related to these contractions. So Alex automatically created this library. So in order to train MTP, please take one of these MTPs from this library and train it. I will show you now how to train MTPs in tutorial. a bit later. So here in MLIP2 folder, I explained everything important. So we also have interface with lamps. Now go to interface lamps MLIP2. Here I also have already compiled LMP binary file, allows us running MTP, but serial version here. In this computer, only serial version. Yes, I should show you, I suppose. We have free, I suppose, public repository. Yes, lamps MLIP interface here, located in gitlab.com. Here we can clone, here are instructions. And also I should show you, yes, MLIP2, after you register, after you fill in the form and register, you will have a link to this repository and you will be able to clone MLIP repository. Here we have license agreement, something like compilation, and a link to MLIP2 tutorials. What is important is the link to MLIP2 tutorials. It's also a free repository. You might directly clone it, don't have to register somewhere, don't have to fill in any forms. Let's find it out. Yes, MLIP2 tutorials. Also, the third folder, this is the third folder. In Wiki, here in Wiki, we can see the description of tutorials we will talk about today. So the first tutorial is passive training of MTP. It's validation and calculation of energy volume curves and elastic constants of BCC molybdenum. So let's go to this tutorial now directly. CD MLIP2 tutorials here. Tutorial number 1. We also, yeah, by the way, as you can see, we have not only tutorial number 1 folder, but we have tutorial number 1 answers. So you may try to follow this tutorial. By the way, everything is explained here, step by step. Prepare an executable file, checking the minimal distance, and etc. I will talk about it. You may follow this tutorial, but you may directly go to the answers folder if you don't want, or just to check yourself. So, but let's go to tutorial 1. So in the first folder, we have training and test set written in MLIP CFG format. Let's go, for example, to train.cfg file. Very simple format. So in the first line, we have number of atoms. Next, we have supercell. Next, we have atomic types, atomic positions, forces. And in the end, I suppose, we have, yes, in the end, we have energies written to this file in electron volts. Positions are given in angstroms, by the way, and stresses. Stresses not per atom, stresses are written for configuration, for the whole configuration, not per atom here in MLIP format. So this is one more important file. And next, now look what's going on here. Here we have calc min dist, so we can calculate minimal distance in the training set. Let's do it with the MLIP comet MLP min dist. So after we calculated it, we have 1.95 angstrom is min dist. So we may specify this minimal distance in the potential. Next, as the next step, we go to the folder training validation error. First, we start with the init MTP. I have already copied init MTP. We specified minimal distance of 1.9, maximum distance of 5 angstrom. Radial basis size is 8 here, and the rest of parameters I didn't change, as I told you. So here we deal with MTP of 16th level. In practice, we typically deal for serious problems with MTPs of 16th level or 20 level, or for magnetic project, we dealt with 24th level. So this is, there we have at around, for 24th level, at around 1,000 parameters to fit. So this is init MTP. I have prepared, yes, of course, in training set, we have a lot of configurations at around 200, as far as I remember. Yeah, 190 configurations, and in test CFG file, We have file test CFG. We have 23 configurations. This is for validation. But I want to show how to train moment tensor potential on simple example, So we can see that train small with small configuration. With train comment, we will read MTP moment tensor potential from the file init.mtp, training set from train small.cfg. Training potential will be written to pod_small.mtp file, and we also will conduct validation on the test.cfg file. And we will run 50 iterations here. So here I simply want to show you how it works. So which output we should see. So train validation. First, this is something like scaling. So here we automatically calculate scaling of moment tensor potential. Now here will not describe how we are doing it. So here I want to show this BFGS iterations. So first we start from 75 iterations. We always conduct 75 pre-initialization iterations of MTP. If we see no parameters in MTP file, yes, here we did 75 iterations, started from 0 to 75. Here we will conduct 50 more iterations. Let's see. Yes, and after training, we see that the errors are very small, but here we had only 4 configurations in the training set. Actually, we deal with 190 configurations. I wanted simply to show you how to train. So here is the output. Pod small is our potential. Let's see what is written there. Pod small. Here we have radial coefficients written. In addition to the previous lines, we have radial coefficients written here, and linear coefficients or moment coefficients here. And of course, constant. We need also, if we fit to DFT data set, we need to use constant parameter in MTP, of course, in any potential also. So we trained MTP. Let's go to the third folder, relaxation. So I have already copied MTP, of course, trained on 190 configurations, of course, this pod MTP. So as the next step, we should run relaxation. So imagine we want to calculate energy volume curves and elastic constants. So we should relax our configuration with respect to both here atomic positions and stresses. So force tolerance is 10⁻⁶ power, stress tolerance is 10⁻⁵ power. We run relax command, also implemented in MLIP, and now we see a new file for us, relax.ini. Relax.ini file. In this file, we specify MLIP settings. This is a so-called file with MLIP settings. Here we need only MTP file name, pod MTP. That is, we don't need anything else. But I will show you why do we need this file, because for active learning, as I show you later, we specify much more settings. So let's run now relaxation. So after relaxation, we have relaxed.cfg configuration. This relaxed.cfg configuration with 0 forces, 0 stresses. Next, we go to the fourth step, energy volume curve. We created, let's remove efs.cfg file from here. Let's remove energy volume file also to run everything from the very beginning. So here I created 21 deformed configurations with extended lattice and with compressed lattice. And here I already prepared the scripts energy volume curve.sh. So we use calc-efs command. We also have calc-efs command, which reads pod MTP. From MTP file, reads deformed EFS, deformed configuration from deformed.cfg file. And as a result, we obtain deformed EFS.cfg file. Let's see in practice. Energy volume curve. Yes, we ran. After that, we have deformed EFS file. Yes, deformed EFS here. Also with forces and stresses written, non-zero already here. So, and we also have energy volume file. I will not draw, of course, energy volume curve here, but we can cut. As we can see, this is energy volume curve calculated with MLIP. This is the value in minimum minus 21.84. And let's compare to the DFT. We also have energy volume curve calculated with WASP. So very close, also minus 31.44, minus 21.84. This is the energy, this is also the energy. Very close to each other. So we calculated energy volume curve, and finally, elastic constants. We can calculate in principle with finite differences directly, but I will show you how to calculate it with lamps. It's better. So here we have lamps. Here we need folder L const with additional scripts. What do I want to demonstrate you here? We have, of course, lamps in elastic script. I copied it from the example in elastic. And here we include potential.mod file. And what is important, in this file, we can directly specify MTP potential that we will use moment tensor potential as the interatomic interaction model. We specify pair style, MLIP, MLIP.ini, and in the second line, pair coef, star, star. So we should simply add these two lines. And after adding these two lines to the file, we can run lamps with moment tensor potential as interatomic interaction model. Again, MLIP.ini file is very simple. Here we specify MTP file name, pot MTP. Let's try to run elastic constants. Yes. Get elastic constants. Elastic. Yes, okay. So here we have 3 elastic constants calculated. Again, everything is duplicated here, step by step, step 5. Elastic constant calculations, 473, 155, 106. Let's see here. Yes, 473, 155, close to this. 106. So in such a manner, we may train MTP, we may carry out validation of MTP and calculate properties of materials. For example, here, elastic constants. This is this example was mainly about passive training, and the very last example, and after that I finish. Tutorial 2. Tutorial 2 is about active learning during MD. So let's go better here, I suppose. Yes, here in MLIP 2 tutorials wiki, we see example active learning during molecular dynamics. So active learning of MTP during MD simulations with lamps. So in this tutorial, we run molecular dynamics of 0.1 nanoseconds at room temperature for BCC niobium. So we will learn moment tensor potential on the fly right now. I want to demonstrate you how to do it. But before this, we should go to the script md active learning mtp.sh, this big shell script. So in this shell script, actually these iterations, I mean these active learning iterations are implemented. So let's probably try. No, this is not good. Okay. Anyway, what?
I don't know. Maybe we can leave some room for questions now, since it's it depends on how much time it takes you for this. But
5 minutes. 5 minutes.
Okay, fine.
Yeah. So here we calculate grades. As I have already told, so we initialize first MTP, calculate grades of MTP, then run molecular dynamics simulations. Then what is important, 2 important models. Step C, we select configurations with selected command. Next, we run, after selection, we run the so-called ab initio calculations, but here as ab initio model, we use EAM, the so-called embedded atom model. as an initial just to test you. But normally in practice, you substitute these strings with WASP strings, for example, and can run molecular dynamics with lamps, but use WASP, for example, as ab initio model, ab initio package. Next, we train MTP. Next, we recalculate state ALS file. This also one more file. I will not explain what is inside this file. Don't have time. It's much more important to run simulation. So I need one more terminal. You will understand why. So now go to tutorial 2 again. CD MLIP tutorials. Tutorial number 2. Active learning. Now we should run this simulation. Let's run MD active learning. Yes, we are running here. You can see training, only training mostly, but I go to terminal 2. What do I want to show you? Here we have training set. Training set, yes. For the moment, we have 12 configurations in the training set. We started from 1 configuration in the training set. So next, again, we are running 13 configurations. So what should I say? During the first steps, I mean, during the first steps of scheme of active learning iterations, normally our algorithm, I mean, our molecular dynamics breaks very fast. So we select and that one configuration during the first steps, because you see for the first we had 12 configurations, next 13, next 18. So first we select, yes, one by one configuration, but at some step we may select at some step after we will have rather big data set, we will select many configurations. So at around at some point we will add at around 10 configurations, probably 20, and etc. So we are running here. We have 25. Okay, let's kill this calculation. I will kill it. Just the final thing I want to show you is tutorial 2 answers. Tutorial 2 answers. So in answers, we have a result of this simulation. So finally, we have moment tensor potential, kern.mtp trained here. Next, we have training set and the active learning state file. Yes, I even have time. In active learning state file, we have active set, written matrix with active set in binary format, by the way, state. Yes, MTP potential first, next in binary format this matrix. So, but better not to see inside this file. This file is not to see, it's just to select configuration. So state ALS, train CFG, and current MTP as a result of this active learning. I think here I finished. So, and we even have, I suppose, 10 minutes or not.
Yes, exactly. 10 minutes of discussion, questions from the audience. Thank you very much.
Thank you.
I see a first question by Felix.
By Felix, okay.
Yes, you can unmute yourself.
Thanks for the presentation. I was wondering why you chose this specific active learning scheme. So did you try out, during the development of this code, did you try out other methods, or you just chose this one and it turned out to work well, so you did not change?
Okay, good question. So it's interesting. Yes, I can explain you. So Alex Shapeyev, it was at around 5 years ago. Alex Shapeyev met Ivan Asiledic, one guy from this university, from Institute of Numerical Mathematics. When I was graduated, yes, when I obtained PhD, they met. They decided to collaborate, and they developed this method. So they use the so-called Maxwell algorithm, which maximizes metrics. So Ivan Asiledic developed it. So Alex also knew about this algorithm. They tried, and after tried, we saw that it works. But of course, we compared with another algorithms. I suppose our maximal algorithm. As far as I know, it's better to ask Alex and Evgeny Podrybinkin, but as far as I know, it works not worse than another algorithms, for example, query by committee strategy. So historically, just because started to collaborate, because he collaborated, Alex, with guy who developed maximal algorithm. So that is historically.
Okay, thanks.
Now we have Edgar.
Hey, thanks for the talk. I was wondering about one thing in particular, which is the BFGS algorithm that you use to actually fit your potentials. That assumes that you've got a fairly straightforward hypersurface on which you want to find the minimum, right? Is that something that you can somehow expect given the the functional form of the MTPs, or have you played around with using, say, non-deterministic, more stochastic methods for?
Stochastic, stochastic, yeah. Nice question. Yes, we also used the so-called simulative annealing in BFGS. It means that at some point, if we deal with bad local minima, we add random perturbations to coefficients. And yes, as we saw, also this stochastic method sometimes helps us to avoid bad local minimum, but of course sometimes not, because again, we have at around 1000 parameters in MTP. So this surface to optimize could be really of unpredictable form. So, but mainly with simulative annealing, BFGS works good in practice.
Okay, thank you. I mean, I assume that it's in general a question of exactly the number of degrees of freedom, which determines the dimensionality of the problem and how smooth or not a surface you expect. And maybe the MTPs produce a fairly smooth surface in comparison to something like an artificial neural network or something where I suppose the stochastic methods are the go-to methods exactly because of these problems with local minima. But
Okay,
thank you.
Now we have a question from Khan.
From Khan, okay.
Yes. You can unmute yourself. No?
You may write if you want.
We can't hear you.
Yeah, we can't, but you can write.
Okay. Okay, so thank you very much for your talk. Recently, I'm trying to use this potential to develop some polymer electrolyte for the lithium-ion batteries. So what I understand is I cannot see much implementation of your potential in polymer type materials rather than the solid crystals. So I'm just wondering that is this potential is enabled to calculate the long range interactions when we try to implement such a calculation for the ionic materials?
Thank you for a question. So I even have a paper on this topic. So we investigated it, of course, with Alex in 2017 or 18, can show you in Google Scholar. So my Google Scholar, I have a paper. So we tried to add, we can see that silica 02 or silica 02 system, or silica, or it's called silica, yes, I will show you. Improving accuracy of interatomic potential, more physics or more data. So we added the so-called charge equilibration model to MTP. Yeah, investigated this system and compared the results. So, and as we realized, charge equilibration model, the main deduction of this paper, that charge equilibration model doesn't help to improve the accuracy of moment tensor potential, at least in automatic manner. So we tried to optimize the Church calibration model coefficients automatically, yes, by adding, where is it? By adding Church calibration model here with these parameters. We tried, but we did not find that it helped. So the short answer, so for the moment, no, these long range interactions are not implemented in the MTP code, but as I saw in many papers, for example, for lithium-ion batteries, the so-called short range potentials also work good even without charges. I saw some papers on this topic, so you may try to use MTP, but again, as you told, yes, as you mentioned, long range interaction was not implemented. So I think try, and after you try, you will understand whether it will work or not.
Okay. Okay. Thank you.
I can share the link, of course. I will share the link in Slack.
Okay. Thank you very much.
So
we have another question from Edgar.
Okay. Good.
If I may, thank you.
Edgar.
So the question I have is quite universal for active learning schemes, I suppose.
Quite universal.
And what I always wonder is that if you, say, perform a molecular dynamics simulation where you continuously check whether your configuration at hand is well represented by your potential or not, and then decide to include it in the training or not, that a priori implies retraining either configuration by configuration or maybe in batches. Presumably, you eventually run into the problem that the actual retraining of the potential is as costly or more costly than, say, a first principles calculation, whatever reference calculation you'd like to perform for your configurations. And that, I suppose, must be subject to how many active set configurations you have, how large your active set is. So can you give me a feeling for whether this is a problem, and if it is, at which point it becomes a problem?
I can answer you. Okay, nice question, very good question. So the first, the size of active set is equal to number of parameters in moment tensor potential. It's always size of active set is equal to. So for example, for the potential of the 1000 parameters, we have active set of also 1000 configurations, yes. But we didn't have problems with this because MTP is a rather fast potential. So, and mainly, yes, the main bottleneck is DFT calculations. But in all projects, except for one project, except for ring polymer molecular dynamics, this project I'm working on, yes, as already was said. So yes, there our for the ring polymer molecular dynamics, our potential is heavy, rather heavy, and the bottleneck is MTP itself. So even several hundred of parameters are too much to run ring polymer molecular dynamics. So in some projects, so in one project, I gave you example of one project in ring polymer molecular dynamics. Yes, we run MTP, the bottleneck running of MTP. But mainly, again, no DFT calculations, it's a bottleneck. It's my feeling from my experience.
Yeah, that makes sense. So I suppose the trick is, as you say, if you have a potential with, say, of the order of 1000 parameters, of the order of 1000 training points, then the retraining is likely to always remain cheap in comparison to the reference calculations. And when you actually apply it, you don't necessarily do any retraining anymore, right? Once you've developed a suitable training set through active learning, you just evaluate. Okay, thanks.
Thanks for the question.
So I think that there are no more questions, and it's 5:30, so we can thank again Ivan.
Thanks.
And then we have like 10 minutes break, and we will start again in 10 minutes with the last talk.
You may continue asking questions me in Slack, for example, or here.